Hi guys, it's Kate and this is the second video for week 2 of Math 23B. Now for using Fubini's theorem. Fubini's theorem is very useful, and our first point here sort of points out what Fubini's theorem says. The casual version of Fubini's theorem says that if a function f is integrable, you can compute the integral by doing n single variable integrals in whatever order you find convenient. Now, what does that mean? Well, let's take a look first at this region of integration. Our chore here is that we're going to integrate a function g, which is x, times e to the xy. Note that this is not a function of x times a function of y, because x is not only a coefficient on e, but it's also up there in the exponent, so we can't just make this a product of a function of x and a function of y. And so we want to integrate this function g over the triangle shown here. And we have two different alternatives when it comes to saying, oh, we can compute the integral by doing n single variable integrals in whatever order we find convenient. Note that for us, because there are two variables, x and y, that means we can do two single variable integrals in whichever order we find convenient. So let's take a look at these two alternatives. Our first option is to integrate over y over the region, using functions of x to determine parameter bounds, and then integrate over x over an appropriate interval. Now, that may not make a lot of sense to you, but let me explain it thoroughly first. And be patient. Setting up these integrals takes practice, but let's take a look. All right, integrating over y. What does that mean? Well, that means that we want to traverse the region in a y-wardly direction. That means moving vertically. As I move in this y-wardly direction, that's how I always explain it, and it seems to make the most sense to me. The first thing that happens is I enter the region, and I cross this particular line there at the bottom. We have to think to ourselves, what's the equation of that line? That's right, it's y equals 0. Every point inside this region has a y value that's greater than 0, so let's write that down. Now, as we continue our travels in our y-wardly direction, we exit the region through this diagonal line up here. And we need to figure out how to express that line in terms of as many variables as we like. We can't use y, but x is up for grabs. And so, of course, if we take a look at what 2 points are involved here, we have 0, 1 here and 2, 0 here. We find that the equation of this line is y equals 1 minus 1/2 x. So we know that this region right here in the middle, the actual triangle itself, is bounded below by y equals 0 and bounded above by y equals 1 minus 1/2 x. Let's complete that inequality. Those become our bounds for y right here. So when it says that we integrate over y over the region using functions of x, note that we're allowed to use a function of x right here to determine parameter bounds. That's what that inside single integral with respect to y is. And of course, just like taking a partial derivative with respect to y, we'll be finding antiderivatives with respect to y when we compute this. Then the next step is to integrate over x over an appropriate interval. Now, how do we do this? The way to do this is to take this entire region, this triangle, and project it straight onto the x-axis. What does its shadow look like on the x-axis? There you go. That's exactly what the shadow, quote-unquote, of this triangle is onto the x-axis. And the endpoints of this shadow give you the appropriate interval for x when it's time to integrate with respect to x. So x goes from 0 to 2. Note that it's really important that you cannot use functions of y to describe x's bounds when you're integrating in this order, because if you had y appearing in the bounds of this part of the integral, you'll be computing from the innermost integral, you'll evaluate that integral, and then you'll move outwards. You'll evaluate this integral. If you had y appearing in these parameter bounds, you would have y appearing in your final answer, which would make no practical sense. You need a numerical value for your integral. And so you'll see the most number of possible variables appearing in the innermost integral. Once you integrate with respect to a particular variable, note that we integrate with respect to y here, you will not see y mentioned again. And similarly, as we move towards triple integrals, if you have x, y, and z, once you integrate with respect to z, you will not see z used in the bounds for the outside integrals. Once you use y, you won't see y appear again. Once you use x, you won't see x appear again. So you want to make sure that only the inside integrals, the bounds of that integrand, will involve variables, not the outside. So let's take a look at option 2. We said that there is another order. Of course, we could do x first instead of y. Now, how do we go about determining the bounds for x going first rather than y? We want to now reverse our approach. We want to integrate over x over the region using functions of y to determine parameter bounds. So that means that we want to move in an x-wardly direction over this region. So we're going to be moving along this path. And already we've crossed a bound right there. Now that is, of course, x equals 0. So we know that every single point within this triangular region, x will be greater than or equal to 0. We continue in our x-wardly direction until we leave the region. And note that we are crossing that same line as before, but now our challenge is that we need to use a function of y to describe that bound. Well, all we have to do is take this and algebraically solve for x, and lo and behold, we will have a function for y. So we get x equals 2 minus 2y as the function that bounds x. So we add that to our inequality. The next thing that we want to do is the same thing that we did for x. Remember our second step when we integrated in this order, when we did y first and then x, was we found the bounds for y using functions of x, and then we projected onto the x-axis. Now we found the bounds for x using functions of y, and then we want to project this triangle's shadow onto the y-axis. What does that look like? There we go. We see that pink interval there on the left is going to give us the shadow on the y-axis, which means that y is going from 0 to 1. Again, we note that we cannot use variables on the bounds on this outermost integral. So these are our bounds for x when we are integrating with respect to x. We treat this as a single variable integral there. That's just a single integral. We're taking antiderivatives with respect to x. We treat y as constant, and then we integrate with respect to y once we've done that. It is not simply swapping these two integrands. Note that the constant outside integrand changes when we change the order, as does the variables used within the innermost integrand. So it takes a great deal of practice to learn how to do this. Sometimes you'll be given a region that's drawn for you or described, and you have to come up with the bounds yourself. Sometimes you'll be given something like this, and you have to go you should go in reverse order in this case. You should look at, okay, if this is dy, these are the bounds for y, and so I can write an inequality like this. I'm going to do this line and then this line, and then I want to take a look at, the bounds for x are 0 to 2, so that's going to fill in the shapes that I have there. So you want to practice both orders, because sometimes you'll end up with a function that can't be integrated easily in one direction, in one particular order. And you want to switch orders, but all you're given is this. So you want to practice as much as you can, going from a picture to the integral bounds to setting up your integral, or going from the integral bounds to these inequalities to your picture as much as you possibly can. That'll give you the most sense of confidence when working through these types of problems. The big result that Fubini's theorem states is that either of these integrals, either the one where we integrate with respect to y first or the one where we integrate with respect to x first, are the same as the double integral of g over the triangle, defined by using dyadic cubes. So we have a choice. These are equivalent to the double integral of g over this triangle. And in fact, you guys probably haven't actually noticed, but you've used Fubini's theorem before. When you did things like calculating volumes of solids by using slices, like washers and cylindrical shells and discs and things like that, you actually were using Fubini's theorem, but The first of the two integrals were really easy. That was taken care of by actually computing the volume of the washer or the disc or the shell. So you probably didn't notice it, but you've been using Fubini's theorem without realizing it for maybe over a year now.